Alright, next tutorial is how to use the UAM equations, also called the kinematic equations, because kin, K-I-N, means to move. And so the kinematic equations would be the equations for motion. Alright, there are 5 UAM variables. If you know, there's 5 UAM variables. There are 4 UAM equations shown over here in the table. If you know any 3 of the UAM variables, then you can solve for the other 2, and you'll be left with one happy physics student. So let's see if we can list the 5 UAM variables. There's acceleration, there is initial velocity, there's final velocity, there's displacement, and there's time. Okay, so if you know any 3 of those variables, then you can figure out what the other 2 are. So let's work some practice questions where we use those 4 equations over here to the side and figure out what the missing pieces are. Okay, here's our first question, and this comes from your notes. Jason hits a volleyball so that it moves with an initial velocity of 6 meters per second straight upward. If the volleyball starts from 2 meters above the floor, how long will it be in the air before it strikes the floor? Assume that Jason is the last person to touch the ball before it hits the floor. Okay, so the first step you need to do in any problem is to always draw a picture. Alright, so we've got the volleyball, and Jason hits it straight upward with an initial velocity of 6 meters per second. Okay? The volleyball starts 2 meters above the floor. So let's make our floor down here. And then we're going to say that our displacement in the y-axis is 2 meters. Okay. Remember, it says right here, Jason was the last player to touch the ball before it hits the floor. So that means that the whole time this ball is going through this motion, the only force acting on it is gravity. And when that's the case, we are talking about an object in free fall. And all objects in free fall on Earth have an acceleration due to gravity, or an acceleration in the y-axis, equal to negative little g. And so negative little g is equal to negative 9.81 meters per second squared. Okay, so we've drawn our picture and we have listed what we know, alright? And you'll notice that we know 3 things about the motion of the ball. We have the initial velocity, we have the acceleration, we have the displacement. So with those 3 things, we can find out what the other 2 are. The remaining 2 UAM variables are the final velocity and the time. Okay? But before we can figure those out, we have to decide what motion are we trying to figure out here. Okay? And it asks when the ball hits the floor. Okay, so if we were to solve for the time right now, okay, then what we would know is the time that it takes for the ball to get to the floor from where it started from. Okay, because the displacement that we know is between here and here. Alright, but we want to know how long it takes the ball to make its full trip. Alright, you know that the ball is going to be hit upward, it reaches a peak, and then it's going to fall back down. If we try and plug this in, all we're going to know is from its starting position to the floor how long it takes. Okay, so that's the next step for any time you work a physics problem, is you need to decide what parts of the motion we're talking about. So here's what I'm going to do. I'm going to say that the ball is going to reach some peak height. Okay, and we'll say that's up here. Alright, now, if we look at this problem and we want to know how long it takes the ball to go up and then come all the way back down, we're going to have to split the motion up into a couple of parts. Alright, so I'm going to say that this can be my initial position. That's the cursive letter I, lowercase. That's the initial position 1 here's the final position 1. Okay, so by setting this as the initial position and this as the final position, I'm saying anything in between here is what I'm about to figure out. Okay, and in between here, let's talk about what we know. We still know that the initial velocity of part 1 here, so I'm going to add a little 1 there to let me know that I'm talking about the initial velocity at the initial position for part 1. We know the acceleration due to gravity is going to stay the same for part 1, and in fact it'll stay the same the whole way through because it's a constant. And then we know up here at the very peak, when you throw an object up in the air, it reaches some peak height and then it has to come back down to Earth. And so in order for it to stop moving upward and start moving downward, it has to cross the 0 line on like a number line. Okay? So that very top velocity there is going to be equal to 0. Alright. So now you'll notice we know 3 things. We know the initial velocity, we know the acceleration, we know the final velocity. The question asked us how long. How long does it take for the ball to go all the way back down? So it's asking about time. So what we need to figure out then is how much time passes from its peak height to its starting position. Now the cool thing about this is that the ball is going to go up to its peak height and then it's going to come back down to its starting position before it goes on the rest of the way to the ground. So once we find out this time interval right here, we can just multiply it by 2 because the ball goes up and then the ball comes right back down. So we can just multiply that section by 2, then figure out how long it takes it to get from here to here, add it all up, and we're done with the problem. So let's go ahead and calculate this right here. We've got our initial velocity, we've got our final velocity, we've got our acceleration, and we are trying to figure out the time. So we need a UAM equation that has these 4 variables and nothing else. It can't have anything else in there. Alright, so which one of them do you think it is? Well, if I were you, let's see, I would probably go for this one right here. Final velocity, initial velocity, acceleration, and time. That's the one I would use because it's the easiest. So let's write that down and plug in. Final velocity equals initial velocity plus acceleration times time. Time is the thing I'm after, so I'm going to have to rearrange here. We're going to subtract the initial velocity on both sides. So we get final velocity minus initial velocity equals acceleration times time. Divide by acceleration on both sides. And time is equal to final velocity minus the initial velocity divided by the acceleration. So now we just plug it in. The final velocity is 0 minus the initial velocity divided by the acceleration due to gravity. Okay, so you'll notice up here we get 0 minus 6. That's going to give us a negative number. We've already got a negative number on the bottom, so those 2 negative signs will eventually cancel out, which is good because you can't have negative time. Alright, and then we need to go ahead and look at our units here to make sure that those are going to cancel out appropriately. So in order to do that, we're going to get a complex fraction. So let's take a look at that for a second. I'm going to give myself a little more space. Alright, so we're going to have meters per second. That's this one right here. That's a fraction. And that fraction there is over the top of another fraction, making it a complex fraction. Alright, now to get rid of a complex fraction, you multiply by the reciprocal of the denominator. And whatever you do to the bottom, you have to do to the top. So down here, these cancel out. Alright, that reduces to 1. Okay, and then here, that cancels, and one of these cancels with one of those, so you end up with seconds over 1, which is the same thing as seconds. And that's really good because we're trying to find time, and so the unit for time is seconds. So that kind of proves to us that we did our algebra correctly. Alright, so the negative signs go away, and now we simply solve. Since we're trying to find an actual answer here, we got to look back up at our givens, and I'll notice that all of the givens had 2 sig figs, so our answer has to have just 2 significant digits. So I'm getting 0.6, need more room, 0.6116 blah 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 blah. Okay, so if I turn this into 2 significant digits, here's the first significant digit, there's the second one. I look at the third place value and see, does it do anything to my last sig fig? No, it does not. So the final answer then is 0.61 seconds. Okay, now that is for our delta t number 1. Alright, the thing that we're trying to solve for. Going up. That's just how long it takes to get from here to here. Okay? Now remember we said we would multiply that by 2 to figure out how long it takes to get from here back down to its starting position. Alright? So, when you do that, you can't just multiply this number by 2 because you rounded it. Alright, we need all of the digits to be multiplied by 2. So I'm going to just kind of pull this up here. Alright, the whole thing on my calculator is 0.6116208 seconds. Alright, and we're going to multiply that by 2 so that we get 1.22324159. And in fact, now that I'm thinking about it, this is not even a final answer, so we shouldn't have even done any sig fig stuff with that one yet. Alright, so this one right here, this number, is how long it takes for the ball to get from the starting position up to its peak height and back down to its starting position, because we've multiplied it by 2. Okay, so let's call that one our delta t1. Okay, and let me put that in here. Delta t1 is going to be the whole thing. Alright, now let's figure out how long it takes to get from its starting position to the ground. Okay, so to do that we need to pick some new points. Alright, we're going to say this is the initial position of trip 2, this is the final position of trip 2. So we're trying to figure out delta t of trip 2 now. Let's list what we know about trip 2. Okay, we know that the initial velocity at the beginning here is not going to be a positive 6 meters per second because at this point the ball is now falling. Okay, this is symmetrical right here, so that means that the initial velocity going up is going to be the same initial velocity right here at this point, except now it's going down. So that's going to be a negative 6 meters per second right there. So let's put that in here. The initial velocity of trip 2 is negative 6 meters per second. The acceleration due to gravity of trip 2 is still going to be negative 9.81 meters per second squared. We know the displacement of trip 2 is equal to 2 meters. And so that's 3 pieces of information about trip 2, and we can find everything else. And what we want to find is our delta t for trip 2. So that means that we need to find an equation that has only these four variables and nothing else. It's got to have initial velocity, acceleration, displacement, and time. So that looks like it's going to be this equation right here. Our displacement, initial velocity, acceleration, and time. Alright? Unfortunately, because we're trying to find time, and we have two time variables here, we're going to have to use the quadratic formula. Alright? Now, there is a way around this. Okay? Now, we're not always going to have a way out, but we do actually have a way out this time. We could find the other missing UAM variable. Okay, like I said, we have these three, and they're asking us to find time. The other thing we don't know is the final velocity. Alright? If we found the final velocity first, then we could use that final velocity, the initial velocity, and the acceleration to figure out what the time is. And we could go back and use this simple equation right here and skip the quadratic formula altogether. You'll get the same answer both ways, but it may actually be easier for us to figure this one out and get the time than it would be to work through the quadratic equation. And since that formula is actually kind of long, there's more chance of you making a mistake if you use it. So I think let's skip the quadratic formula and go without. Let's figure out what the final velocity is down here for trip 2 and then use that. So we're going to say the final velocity of trip 2 is equal to the initial velocity of trip 2 plus, and let's do squared plus 2 times the acceleration in the y-axis times delta y of trip 2. Okay, so the final velocity then of trip 2 is going to be equal to the square root of, okay, because we're getting rid of the square there, the initial velocity squared, so I'm going to put that in there, plus this piece right here. The acceleration due to gravity is negative 9.81, and 2 times that is 19.62. Alright, and then our displacement is going to be negative 2 meters. And it's negative 2 meters because the ball is traveling downward, it's falling. So remember, displacement has direction. Alright, so now we can plug that into our calculators and get an answer. And because we're going to be using this final velocity to figure out what the time is, we're going to need all the decimal places. Alright, so let's get that. Alright, so I'm getting 8.6740993 I'm going to have to extend down here. 376880577. And since we're getting a velocity, we know that the units are going to be meters per second. Okay. So now that we have this, we can use it to figure out the time using that simple equation. So let me get some more space. Okay, we'll come up here and we'll say the final velocity is equal to the initial velocity plus the acceleration times time. So here we're trying to figure out time. We're going to have to rearrange to that same equation we did before, where time is equal to the final velocity minus the initial velocity divided by the acceleration. And this is all for the second trip. So we're going to say the final velocity is the number we just figured out, 8.6740993768805. what was that? 0577 meters per second minus the initial velocity. Remember, the initial velocity is -6 meters per second, and it's negative because the ball is falling, divided by -9.81 meters per second squared. Okay, let's take a look at units. Meters per second minus meters per second gives us meters per second. That's like saying, I've got 3 apples, I take away 2 apples, I'm going to be left with 1 apple. The unit doesn't change in addition or subtraction. Alright, and so we're going to have meters per second on top over meters per second squared on bottom. Same thing happens that happened last time. You end up with seconds. Alright. Now, one thing that you will notice is that we've got a positive number here. We're going to end up adding. So we've got a positive number on top. We're going to have a negative number on bottom, which is going to give us a negative time, and there's no such thing as negative time. But we're going to ignore the negative sign. Remember, these negatives here are only there because of direction. Alright, they're not actual mathematical negative signs. So, let's plug all that into our calculator. Alright, so when I plug that in, I get that T2 is equal to 1.4958307213945554 seconds. Okay? And they wanted the total time, so we know that the total time is going to be equal to each of our individual times added to each other. So, let's see here. We're going to add this number that we just got to this number up here that we got. Okay, so when I add all of that together, I get 2.71907 and then some other stuff after that. Now we can do our sig figs. So here's the first one, here's the second one. This third place value does nothing to our last significant digit, so our final answer then is going to be 2.7 seconds. It takes the ball 2.7 seconds to get back down to Earth. Alright, now I know that that seems like a lot, but that's because I went through every single step methodically with you. Alright, and I explained how we were doing what we were doing. But ultimately, that's going to end up becoming a really fast problem because all you're going to end up doing is picking your initial and final positions, listing the stuff you know, seeing if you know at least 3 things, and then find the other stuff that you're being asked for. Alright, we'll come back in another video and do some more of these.